I'll just share a very brief what's kind of bio of Dr. Sukumar sir. So, Dr. Sukumar Kamalasadan is a Duke Energy Distinguished Professor of Electrical Power Engineering at the University of North Carolina at Charlotte, and the Director of Power Energy and Intelligent Systems Lab within the Energy Production Center and Infrastructure Center of UNCC. And he received his PhD from University of Toledo, Ohio in 2004. And he has his research interests including data-driven approaches to power grid technologies, modernization, smart grid, microgrid. So many things in his pipeline actually, and his basket. And he has been in research for the last 15 years. And his research and methods has been having high-level impact in electrical utility modernization, with very high technologies in modern grid management and control integrating with renewable energy and storage. And he's the chief architect of Duke Energy Smart Grid Laboratory at UNCC. It's a $5 million facility. And coming to his IEEE profile, he is an associate editor and a paper review chair for transactions in industry applications, editor of IEEE transactions on vehicle technologies, editor of Elsevier Journal in Electrical Engineering. And his accolades includes so many awards, recognitions, including the National Science Foundation Faculty Early Career Award, Best Paper Awards in so many years, Outstanding Teaching Awards in many years, and he's a senior member of IEEE, and he's a past chair of IEEE Lifelong Learning Subcommittee, inaugural chair of Election and Quality Control Subcommittee, which selects webinars and tutorials for IEEE Power and Energy Society, and he's a member of Best University Chairs, and he's a member of so many task forces, co-chair for some task forces, etc. And he's a past member of Engineering Systems Subcommittee, vice chair of IEEE IAS, Industrial Automation Control Committee, vice chair of IEEE PES Power and Education Society Committee, and past chair for IEEE PES Charlotte section. And on academic side, he's a very great achiever. On academic side, he has graduated for advising more than 20 plus MS and 30 plus PhD level research students, and plus is a great publisher, and he is having so many publications with citations reaching up to 2,000 plus. I just read his Google profile, and he has authored a book like a monograph type and has 2 patents his credit. And sir, it's really a credit and honor to be introduced you to this seminar. And please, over to you, sir.
Thank you. Thank you all. First of all, thanks for inviting me to be a part of this webinar series and present the research work as well as educational work related to smart grid. And then thanks for organizing this webinar and to be part of this esteemed group. So I'm going to share my slide. Maybe see whether I can see that. When I share my slide, I will not be able to see anything else. Can you see my slide? Okay.
Yes, sir. Yes, sir. It is visible. We can continue.
Okay. All right. So today we were discussing, Varughese sir and I were discussing about the topic appropriate for this webinar. So today we thought to have some introduction to you all on smart power grid technologies and the educational approaches that we use to do research and education on smart power grid technologies. So my name is Sukumar Kamalasadan. I'm a Duke Energy Distinguished Professor at UNC Charlotte within the Department of Electrical and Computer Engineering. I'm also the director of the Power and Energy and Intelligent System Laboratory. What I will do is I will give you a brief overview of my activities related to power grid in general, and also onto the power energy society-related activities and other societies as well. So, but part of mainly we were part of two societies: Industry Application Society and Power Energy Society. These are my main societal level, work. Under the PES, I am the vice chair for the Power and Energy Education Committee, which actually looks into the educational activities of Power and Energy Society. And I'm also technically affiliated with the task force and some other committees, and the latest being Power System Oscillation Task Force, being group chair on that, and the Battery Energy Storage Management Task Force. So these are the main two task forces which I'm currently affiliated with, have some previous affiliations in other task force. My research background is on power systems in general, of late on smart grid technologies, specifically renewable energy integration to the power grid. And the specific part of the research there is power system management and control, device level and system level control. Basically, in the device level control, my focus is on inverter-based control applications and the renewable energy integrated power electronics based control applications. That's one part in the control side on the device level. On the system level, my main research focus is on management aspects of power system. So in today's talk, I will be touching base on the technologies on power grid or power system level, and then I will also touch base on what are we doing with educational level advances, both in research as well as the education aspects, to actually facilitate improving these technologies in the educational arena. So these are the main two parts that we'll be focusing on. A brief overview of a project that we are working on currently. We have two different type of projects that we call it. One project related to fundamental research. This is in US, mainly supported through agency called National Science Foundation. So in that part, the main research work associated with that is bulk power grid monitoring and control. That's one aspect. And the second aspect is renewable energy integration on the form of distributed energy resources. So that is a fundamental type of research that we are focusing on, supported by National Science Foundation. The other type of work, so recently I have an award from Department of Energy that is more on applied research. In this research, we mainly focus on integrating the applied research topics. One of the main topic that we are currently working on under DOE project, which includes 4 other universities and 1 national lab and 2 industry utility affiliation. I'm the lead for that project. So that project is on grid-tied inverter control for managing critical loads, PV photovoltaic related applications or DER related applications, and energy storage applications related to supporting critical infrastructures in the power distribution system. So that is a $4 million project that currently we are working on. We also have support from the utility nearby in Charlotte. It's one of the largest utility in the country called Duke Energy. The goal on that project, we are working on UPS related applications, where that UPS can be used to support critical load and also support the grid. So it's a new technology. So we have a patent associated with that, and we are working on that project. So these are the few projects that currently I'm affiliated with. So this main deliverable of these projects are disseminating knowledge to the audience under whoever is reading, mainly through publications and patents. So the publications and patents we generate, that most of them are done by researchers within the group. In the introductory statement, we have 40 research members who has been a part of the lab, affiliated or graduated. So they under their leadership, we have published several journals and transactions papers, as well as conference proceeding papers. And like I said, the projects are supported by national agencies. So in the presentation, so these are the brief introduction. In the presentation part, I try to divide the topic area on technology advances into two or three main buckets. One, I call it global trends related to power grid technologies, global emerging agendas, especially related to low carbon goal and the effect of that on decision support systems. And then I will move on to two type of power grid area that currently is being talked about as transmission systems and distribution systems. So we are now moving into a new era of power grid management, which includes transmission and distribution system together. So we talk about the decision support and control on transmission system and decision support and control on distribution system, and then we'll summarize that. So mainly I want to introduce a slide that showcases the changing landscape of electricity infrastructure. So in the infrastructure wise, as far as power system is concerned, there has been a very big change that has been happening of late. So I wanted to summarize that, try to capture this. A little bit busy slide. I'm trying to go through that in a little bit in detail. So the key infrastructure change in the power grid is mainly related to two aspects. One aspect is to move the power grid into a sustainable power grid. Sustainability means that the power generated and used in the power grid has to last long and also has to have less impact on the environment. So that's the first main initiative. And under this initiative of sustainable energy, the main goal is carbon footprint reduction. And the proponent there are renewable energy related power generating source. And the second proponent there is what we call it as e-mobility. As you all know, that the infrastructure related to mobility, transportation infrastructure, how you can make that which means that it could be energy intensive in the form of electrical, or it could be environment. It can stand for anything that is that says that it is sustainable. The second part of the main transformation in electricity infrastructure is related to the digitized devices on the power grid as a whole. So these digital devices comes into two forms. One, we call it a system or devices that are intelligent and that can be used as electronic control. So those devices normally can span in different parts or different areas in power grid. But there is a big trend in having those devices at the edge, meaning last point of the power grid, and that is considered as grid edge devices. So the development of this grid edge device has a different meaning towards the electricity infrastructure. And that is because this grid edge device now are able to manage and control by itself. And you get a lot of information from those edge device, which is sitting at the edge of the power grid, which makes the management and control of the power grid different or much more different, right? So the effect of these is what we can call that these edge device can be passive, which means it absorbs energy or power, or it can be active, which means it can deliver energy or power. So this makes this whole power grid, especially the power distribution system, as intelligent and active. So that is the effect of the grid edge devices being electronic and intelligent, making the whole distribution system of the power grid intelligent. And since that is intelligent active, that distribution system, the power grid with these devices can change, can be managed better, so that if there is a problem related to the infrastructure, such as the impact on storm coming in and then power going out, or a cyber-related attack coming in, we can manage that infrastructure such that it is more resilient, and you can keep the lights on for what we call it as critical loads, especially for hospitals and schools and things like that. So that is the second part, having the devices being intelligent and electronics. So there is a word called IED, intelligent electronic devices. So those devices being intelligent or being smart will help improve this. Now, with this, there is also a change on the bulk power grid. And there are mainly three changes that I wanted to bring to your attention. The first change is bulk power grid monitoring systems help to manage the asset and optimize it properly. One of the main monitoring device in the bulk power grid, which has happened for the last 15 years, is under the umbrella of sensing of those power grid, and that is normally done through a device called phasor measurement unit. So this is a big change that has happened on the power grid with the advent of PMUs, or phasor measurement units. So that will help the power grid management, bulk power grid management, important. So that's one aspect. The second aspect, since we can manage it better, we can manage the market of the power grid and make the power grid as a commodity, which can be delivered with less cost and useful to the customer. So that's the second change. And the third part is that with the help of these measurements and sensing, we can change the architecture of the power grid and then be able to manage, protect, and control the power grid better. So this is the basic technological advances in the power grid as a whole. So basically, the phasor measurement unit, which is sensing unit, which happens on the power system as a whole, and sensing-based monitoring and control and management related to that. Number two, devices that are intelligent and electronic, especially on the last points on the power grid, called the grid edge devices, and the effect of these grid edge devices to manage or make the power distribution system more active. Number two. Number three, moving towards sustainable energy initiatives, especially on two fronts, one on renewable energy related energy sources, and the second on the e-mobility. So I just wanted to summarize this in the form of one slide. So the later part of this discussion, I am just going to focus mainly on the few technological aspects related projects that we are doing and how we are doing that in education, being the seminar or webinar being on the educational side. So the first part, I will start with the renewable energies, which are very important and sustainable future. And the move towards low carbon network. So transitioning towards a low carbon network is becoming a mandate across the world, for that matter. So this gives you a brief sketch on renewable energy integration and the comparison of renewable energy with respect to the other fuel sources across the globe. Start with the US, primary energy consumption of the energy sources in US in 2019. As you can see that the renewable energy-based sources are becoming more and more active. So the push towards that is to reduce the carbon footprint, obviously, and then make it more sustainable. The bad news or the challenge is that how do you manage these renewable energy resource integrated power grid? Now, what is the problem? The problem is that these renewable energy resources are what we call it either intermittent or variable. Intermittent means that it is changing its power generation very fast in a smaller time period, especially attributed towards photovoltaic related renewable energy resources. That is intermittent. Now, variable meaning, of course, it is changing with respect to time, not that fast like intermittent, especially attributed towards wind-related energy resources. So both will make that the power coming out of these energy sources are not dispatchable, meaning if I want 1 megawatt, I'm not going to get 1 megawatt. I may get 0 or I may get 7. So how do you make these energy resources dispatchable and we can operate the power grid much like we used to operate it before as a dispatchable energy sources is the main challenge. So to do that, we may need another resources like battery energy storage. We may need a management method to control the inverters, which is coming at the back end between the energy resources and the power grid and things like that. So that is the basic challenge. So we do have obviously high penetration of, we call it penetration of renewable energy resources, and the high penetration of renewable energy resources in different places. A few examples which I've shown in here. And we are moving towards 100% renewables, the so-called, by 2050, in almost around 139 countries have adopted that mandate to move towards 100% renewable. This actually has a lot of impact with respect to the job creation, with respect to the new job coming in, and also we may lose jobs which we used to have before. A new type of jobs comes in. And there is also, we may need to have a trend to have inequality in jobs or equity in jobs, meaning that we don't want only have these jobs going to some countries and not this job going to some other countries. So it's our focus to make sure that such advances in technology stays in our countries and create jobs in our countries. Otherwise, there will be an equity problem related to jobs having in different parts of the country across the globe. So that's another part that is critical. So whoever is advancing this technology and moving ahead faster will be able to create jobs faster. So it's now kind of a race towards that. So you may be already seeing these kind of trends across the world that some countries will have more advantage towards having more jobs which is related to renewable energy resources. So that's another part. So working together as a group to share the technology advances, exchange that to different people, and making sure that we indigenously develop that technology advances, right from education towards research, towards generating resources for people to learn these technologies is our job, to me at least, what I feel, to support the next generation workforce. So 100% renewable energy push is there, it's coming, and of course we are seeing that. So what I wanted to focus on is that what are the required changes that we will be doing on decision support and controls, especially on this. But you also see there are some changes and challenges associated with the natural disaster, artificial disaster, or pandemic, or whatever you call it. So you can see there are very, very severe, clear indications on weather-related pattern changes. You can call it climate change, or you can stay away from it and call some other words, but it is very clear that the weather-related patterns and changes are imminent, and it is coming. Not only weather-related pattern change, it's also very clear that the lifestyle, health-related aspects, for example, pandemic, this is part of our life now. Now, what is the take of that with respect to the support system in technological advances related aspects? Well, we should be able to be having the systems make changes and aware of these weather-related pattern changes and adjust accordingly, technology-wise, human management-wise, and human interaction-wise. So The few things which you said, these are, earthquakes and patterns and the calamity related to that. And this is specifically related to the electricity demand, which changed during the pandemic. This is in northern Italy, and you can see that the trend that happens during pandemic, power going down and power going down, the cycle related to the load patterns, all those things are now becoming a new trend or new change now. Some for good, some for not for good, but we still need to make sure that we accommodate these changes and then have the system support according to that. Now, what are the kind of support that is critical now? There are mainly four main aspects to make sure that the systems are resilient, we call it, or the systems are actually going to fail safe, or going to take care of these natural hazards or calamities. The resiliency part has four main attributes. One is speed, second is the selectivity, third is the sensitivity, and the fourth one is the sanity. So as you can see in here, there is one graph that I want to portray. What we call it resiliency. Resiliency is attributed towards, by the way, I don't know whether you all know this or not, but resiliency is attributed towards having how the system behaves when there is a problem. After the problem happens, how do the system respond to those problems, and how do we come back during that problem, or fail safe. Fail safe meaning we are failing, but we are making sure that the critical part are being taken care until the last point of failure. So that is basically what we call it as resiliency. So you can see that the normal operating condition, and we call this is a resilient states or a robustness or resistant states. And after that, you actually has the resourcefulness or redundancy. You're actually doing self-organizing with respect to the event. And as the event progresses, we are at a point that is a degraded state for that event. It's a post-degraded states. And then we're going to restore back to this we call it restoration phase or response recovery state. And then we will have a post-restoration states, and then come back to the infrastructure recovery state. So in all these things, the key four main attributes are speed, shortest time for the equipment to be taken care of or out or come in, avoiding extended equipment stress, selectivity, elimination of the bad part of the system, how fast you can do that, sensitivity, fast detection of low, high magnitude of faults on the power grid, and obviously the sanity, which is dependability of the system and making sure that you can depend on the systems at all points of time to make sure that the minimum part of the system is isolated. So with this in mind, now what I'm going to do is I'm going to jump in and talk briefly about two main power grid related aspects. One on the transmission system, call it bulk power grid. There the focus is on photo PMUs based systems or sensors, and how that is used in the bulk power grid on phasor measurement side. So that is one topic that I want to pick for today's discussion. And technology advances in that, how we do educational project related to that. And then we go in the distribution system, we'll touch base a little bit on distributed energy resources, energy management, and the project related to that. So the decision support system on the bulk power grid, for that matter, is based on telemetry, which is coming out from the different parts of the grid through a group or a system called SCADA, which is supervisory control and data acquisition system. So basically the SCADA telemetry information comes to a main center in the power grid, and that main center operator will manage the power grid based on that. And the management of the power grid is done through load frequency control, which is active power management, and very little reactive power management, mainly on the power grid side on voltage stability or voltage management on the generators, called excitation system management. So what is the change now? Well, the change is that because of the advent of renewable energy resources on the power grid, on the bulk power grid, we have resources in different parts. But not just that, on the distribution system, a lot of distributed energy resources on this system, right? So the whole power grid now cannot be operated in silo or transmission and distribution separately, has to be connected together. And the infrastructure has to be modeled as one. And that change in modeling, which is very important in classroom, especially on the educational side, to model the whole grid as T and D infrastructure. Now, what is the problem there? The problem is that we never used to model the transmission and distribution of the power grid in the same way. That's the biggest problem. So if you may know, if your fundamental power grid courses in the classroom and educational side, transmission side of the power grid are, we call it balanced, which means that there is no three-phase. There's only one, positive sequence ways of representing the power grid on transmission side. On the distribution side, we have a three-phase system. We try to model it balanced as much as possible, and towards the last point on the power distribution system, like these laterals, we may even not model, or even if we model on three-phase. So all are like a different type of modeling in different parts, but they are not integrated together. And there is no way of integrated modeling them, and there is no methods or mechanisms to do that. So that's the first main change. That's on the model side. Now, on the management side, there are managements on the power grid done in two different parts separately. The bulk power grid is managed in what we call it EMS, or energy management systems, and the distributed side, the power grid is managed what in general called DMS, distribution management system. But that is going to be changing. We need to have management done connected together. First, we need to have an integration between EMS and the DMS, number one. Number two, we should have more management systems on the distribution side, which includes community energy management system, the distributed energy management system on the DMS side, demand side management system, then advanced meter infrastructure based management system. So as you can see, there are bulk boxes coming on the distribution side at each level, user level, distribution system level, and the bulk system level, and that has to be correlated together. So this is a big transitional change, one on the model side, another one on the management side. And it has got impact with respect to what we call it time sequencing. We should be moving the time which we used to manage these resources in a different way. For example, economic dispatch of the power grid in 4 to 10 seconds, state estimation 1 to 5 minutes, the contingency analysis. So these are functions which used to have, I am not going to each one of those blocks in detail. And yes, as you may know, these are the functions which used to have originally in the power grid. Now we'll have new functions: distributed energy resource management system, distributed resource management system, AMI synchrophases capable relays, and the phase measurement. So on the transmission side, the time of those management systems are changed. On the distribution side, new management systems have emerged. So the way that you model, measure, monitor, and control now has changed because of the advent of phaser data or phaser measurement unit. So it used to be SCADA-based. Now we are going to have a measurement-based management system. The good news is that you can measure it and manage it faster with a faster time frame. The bad news is that you should be able to have enough resources to manage and control those devices with the measurements. So one of the way that has the measurement and control has improved based on the phaser measurement unit integration is what we call it as a wide area control. Wide area control means because of these measurement devices like a phaser measurement units in different part of the system, we have a capability now to actually monitor and control the grid as a whole, not as a different part of the grid. So in general, that term is known as wide area control or a coordinated control. So in the lab setup, this is a lab wide area control setup that we actually has been implemented at UNC Charlotte. It includes the power grid models that we can generate, transmission distribution models together. We have a phaser measurement unit which can come in two forms. So these phaser measurement unit these days, it can come as a part of relays on the power grid. For example, this is a relay which is SEL, Schweitzer Engineering Laboratory 421. This relay can have a phaser measurement or synchrophaser block I'm not actually going through and then explain what is a PMU. It's like a one seminar by itself or webinar by itself. So the phasor measurement unit, the capabilities that it can actually get phasor data of the power grid time synchronized, which means phasor data at different points in the power grid can be plotted at the same time, which gives you that phasor voltages and current waveforms at different points and how they are aligning together. What's the good news? The good news is if they actually has a change or a shift, and if that change or the shift is staying constant, we know that the grid is healthy. But if these waveforms or the change and shift is moving, which means there is a problem in some part of the grid. So that is a very, very big thing. You can actually diagnose like your heartbeat. You can exactly get what are the different changes in different parts of the grid. So we can use a relays and then collect the power phasor data at different points. On the hardware side, we can also get it through the software. And one main simulator that we have, which we use in the lab for educational purpose, is the real-time simulator, which you can connect the hardware part in there, and then you can collect all that information into a central hub. It's also what we call it the phasor data concentrator hub. It's also provided by a company like a SCL. And then you can monitor at different parts of the grid. So this can be used for dynamic security assessment, energy management, synchrophasor related applications. So we have a couple of work done and published related to this. And I'm going to talk about that work that is related to oscillation characteristics and oscillation monitoring. Oscillation of the power grid is a very important part, and that can be captured through, like I said, using the phasor data concentrator or phasor measurement unit. What do you mean by oscillation? So if you look at a power grid which changes with respect to time, and 24/7 the load and generation is balanced and we are moving with respect to time. Now, there are changes which happens on the grid, which happens internally or externally. For example, fault. So suppose there is a fault or outage, there will be oscillations. And then oscillations dies out, and then it changes, and it happens. So these are oscillations in different parts. For example, this is in the Western United States. Two oscillation happens. Zones are one on the north and one on the south. You can see that at some point of time, this happens in 1996. We have at one point, the oscillation happens and then oscillations are not died out, and it increases the speed, and then it creates what we call it as outage or tripping of the generator, and continuous tripping of the generator called cascading. So there are several instances of blackouts, and we have some instances in India also, as you may already know. So this is, it is going to come. You cannot avoid it. So what you can avoid is how can we actually monitor the grid and then manage it. So in order to monitor, first we wanted to make sure that these oscillations, what we are seeing is actual, not that created. So this is a difference between the real actual oscillation and what you see in a model if you are not using phasor measurement unit. And as you can see that the real oscillations are like this, but the model says that there is no oscillation. This is because of the reason that we are not able to capture those dynamics or changes fast enough, and also not be able to model it properly. So what the phasor measurement unit does, it actually helps us to see these oscillations happens very clearly and exactly well. So these are one of the initiatives in the United States for improving phasor measurement unit. India also has a big initiative, which I know last 2-3 years been happening. I don't know what is the status now, to implement phasor measurement units in different part of the country. So these phasor measurement units, these are in the different part of the country in the US. And the advantage of having this phasor measurement unit is actually to see the data which is coming in, and you can see that comparison of PMU and phasor data, SCADA data, PMU data, these blue one see all the oscillations, but the phasor related data coming from SCADA don't show any oscillations. So what you do with this oscillation detection? What do you do with this oscillation detection? In the lab, we actually set this oscillation monitoring, and you can actually tap these oscillations in different points on the grid also. And if with that, in the lab, we have this, so this entire setup, what I'm showing, I'm not showing exactly for this project, but for the entire project. So we have real-time simulators interface and the model that can be modeled for the renewable energy resources through a modeling platform from Typhoon. And then we have interfaces which can be used to model distribution system and transmission system separately. So what do we do with these oscillations? Well, we can do, the first thing is characterize these oscillations. And we can talk about whether these oscillations are coming within the power grid or external to the power grid. This is an example. With these oscillations, you can see that modes of oscillations, the damping percentage of oscillations, and the oscillations are whether it's coming from internally or externally. So with this new framework that we developed recently is to monitor these oscillations, whether it is internal or external. I'm not going to go in very detail about this topic, but I'll give you a brief overview. Internal oscillations are called natural. That is divided into two parts. One, we call it ambient, which is related to changes in the load. And the second one is a ring down, which is related to the changes in the fault. So there will be ring oscillations and then dies out. The oscillation which is coming external to the power grid are categorized as forced oscillations. It necessarily doesn't mean that it is external. It could be because of malfunction of the controllers in the power plant. That oscillations, when it happens, you will see, like, for example, a cyclic change, and there will be oscillations which is going up and down, and it may damp or it may not damp depending upon the system. So what we can do is we can classify these oscillations. This is a ring down. This is ambient. These are actually the forced oscillation. You can classify the oscillations, the frequency of oscillations, and also you can see whether forced and natural oscillation comes at the same frequency. We call it resonance. How do you divide them together? So a few examples that I wanted to showcase. And this oscillation characterization will also, the second part of it, is to see the location of these oscillations. Where are these oscillations coming from? Which part of the power grid is more vulnerable with respect to oscillation? So that is the second part of tracking the oscillation modes and coming from which part of the power grid the oscillations are coming from, to identify those. So these are two main examples there. So that's the first topic related to PMU and the sensors. The second main part which I wanted to bring into your attention is power distribution system. So this power distribution system integrated model, normally it is 69 kV and below, and we have a lot of renewable energy integrated systems on the power distribution network. So the decision support of the power distribution system, like I said, is changing. We have new ways of managing the power distribution system. One for renewable energy resources called DERMS, Distributed Energy Resource Management System. And the other one is called Advanced Distribution Management System, which includes the customer management systems, home energy management system, field automation, of course, outage management system, and GIS-based management system. So this is basically the decision part of the systems now changing. We have management and control associated with the decision is also changing, which related to the communication systems and the latency and bandwidth associated with that. So this is a architecture of how the management and communication and control aspect of the power distribution system is changing. If you can see, just want to give you a sketch. You can see that it's advancing quite fast, and you can see there are changes happens at the switches level, on the device level. Now these are all called IEDs. Like I said, remember that I was telling about the grid edge device called IEDs. So you can see smart routers, smart reclosers, and also you can see customer level, consumer level, devices, communication infrastructure integrating that with respect to the substation and then at the back end. So on the distribution system in the lab, we create distributed energy resources like a PV simulator loads as a energy source, and then you connect that to the power distribution system through the power amplifier, and this helps us to integrate the hardware in the loop setup, and then we can have our control architecture done through substation and substation automation. So these are the main educational aspect that I wanted to bring in. We can have software integrated to it. So these are few commercial grade software that we have in the lab that has been integrated to that to study. And the project that we are currently setting up has a lab component where you can see the details of the project, right here in breedespv.org. So this project is, like I said, from Department of Energy. The goal is to create resilient control for real-time photovoltaic dispatch to manage critical infrastructure. So in this project, what we are doing is we are looking at power distribution system, controlling the devices in the power distribution system, which is mainly DER or distributed energy resources. One part is renewable energy, another part is battery. And control happens through the system setup in the lab. So here is an example. So this is a lab setup. We are actually sending and receiving signals from the field, from the utility to the lab to control these devices. Which device? Battery energy storage and photovoltaic farm. So what are the use cases that we are working on? One is obviously managing the power grid to reduce probably the total losses. This is done through an architecture called distributed optimization. So here is a power grid example, and the renewable energy connected at different points on the grid. And the goal is to manage these DERs and support the power such that the total losses on the power distribution system is minimized utilizing an algorithm. And this is voltage profile associated with that. The second part is to manage the DERs in the distribution system to track that set points set by these, optimal power flow. So tracking the set points will obviously reduce the total losses. So how are we managing them? We are actually looking at the distributed energy resources, PV, and the batteries in the form of group. And we call it cluster, fictitiously, meaning virtually. There is the real hardware in the field don't know I am a part of the cluster. But after we make them the part of the cluster, will give dispatch set points to the devices in the field, and the devices, when it sends the power using the dispatch set point, will be able to maintain the total overall objective of reducing the losses. So that is basically what you can see in here, it tracking the losses. This is without a control, the gray, and this is with the control. And this one is actually to make sure that the distributed energy resources, locally, they are working in the groups. And there is no power, minimum or maximum power reduction in the total power between the groups. So that's basically the another use case. And the third use case is to minimize the voltage profile on the power distribution system by managing what we call it as net load. So net load is basically, as you can see, that because of the photovoltaic being intermittent and we want to extract the maximum power from the photovoltaics, you will see dips and bumps in the total load on the power distribution system. In general, in the larger level, this is called duck curve because this looks like a shape of a duck. As you see, this is what we call belly of the duck, and this is the head of the duck, and this is the tail end of the duck. So this happens because of the photovoltaic, which happens in the middle part of the day. And the goal is to reduce the belly of the duck and to make it more flatter by having the support from maybe battery energy storage. There's a real bad news of having this belly being like this because that extra power that is required to maintain this has to be taken from the conventional energy resources, and cyclic power plant, we call it, cyclic generators has to be acting along with for this purpose. So that's a big challenge. So we can reduce that by managing the net load or locally managing each distributed energy resource. That's one of the use case. And finally, the use case is on the voltage profile. As you can see that the voltage profile and power distribution system needs to be balanced. It's like a pipe not being clogged so that the water can flow through the pipe. So our goal was to balance it as much as possible, utilizing the reactive power coming out from the inverter, which is kind of free, which if you have more capacity as far as inverter is concerned. So this is one example where you can see the voltage profiles are balanced. And this is an example that we showcase when there is an intermittency in the photovoltaics because of the outage on the PV farm. how you can manage the voltage profile as in here, as well as the power profile. So that is basic few work that I wanted to showcase on the distribution system. And obviously, this advances in the distribution system is more and more going towards the field device, and device automation and device level control as becoming very, very prominent. So the future of this distribution system management depends upon how effectively we can control or manage the devices in the field and on the substation level. So that is basically the trend. So and this is coming under the umbrella of what we call it ADMS, or Advanced Distribution Management System, which includes a repository of those things which you can call volt-war control, alarm residual. All these things can be implemented in the lab and then given as an educational resource. So to summarize, for the grid with renewable energy resources and the decision support system and the advanced educational test bed that we can manage, I think there are mainly 4 or 5 main parts that we should focus on. One is on the wide area control and bulk power system with phasor measurement unit. We should have some ways to educate people and then develop workforce in that area. Second one is the decision support systems on the distribution system, which is DMS and ADMS. We should have control approaches and the automation approaches related to field devices and the management of the system. The third part is the modeling of the power grid in the classroom. When we are doing educational work, we should maintain or showcase how the co-simulation models of the transmission distribution can be implemented, and how that ties with respect to what we call reliability and resiliency. And the last part is the grid edge devices and management and control with the renewable energy integration. So these are some of the technological advances and the educational tools that we can develop. So I just wanted to stop, maybe a sense of time right here. Hope I tried to bring that and then maybe entertain some questions.
The questions are there in the chat box, or you will be reading? Somebody will be reading?
Yeah, unfortunately, when I start presenting, I cannot see, even face. I don't like, without seeing face, it's hard to, present to the computer, but I could not read if there is any question there on the chat box.
Yeah, somebody will read it. Eldo, you can read it now. Okay. Let me have a few questions, sir. One I have found is, see, when the renewable energy percentage is getting more and more, is there any optimum percentage of DER versus storage? That's the question number 1. I have one more question. Another one is, see, places like US, the grid is supported by many suppliers. These suppliers will have different quality, different pricing, and different configurations. How do we manage?
What was the last part, Dr. Varughese?
In the grid, like grid for countries like US, it is supported by many suppliers. On same grid, there are many suppliers with a different pricing. So how do we control the quality of these different suppliers?
Yeah, so the first one related to the battery energy storage. So there are 2 parts. One, what we do for the DER is something called the hosting capacity calculation. So hosting capacity means that how much of the DER can be incorporated in the power distribution system, not just because of the thermal rating, we call it, which is the capacity related to power, but also related to voltage balance in the system. So there is a study that performs to see how much of the renewable energy resources can be connected to the power distribution system. This comes in 2 parts. One, obviously, on the visible renewable energy resource, so call it, which is in front of the meter. what we call it. And the second one is behind the meter. Behind the meter is much more difficult to study because it is distributed and location-wise it is different. So that is the first part. Now, the second part of that study is what type of battery energy storage, what size of battery energy storage will help to support the DERs on the system. The rule of thumb generally is that if you have a 30% capacity battery energy storage, 30% compared to the capacity of the photovoltaics, that 30% battery energy storage capacity is good enough with a 3-hour energy storage framework is good enough to support or even out the intermittency related to the photovoltaics, not the nighttime storage, but in general, with the intermittency related to photovoltaics. So that's a rule of thumb, but that's not applicable all the time. We may need more or less in different locations at different point. So what we do is an optimization study with the battery energy storage included on the system to see how much of the battery energy storage is needed in general, which is actually mandated by the utility to support. So that's basically the two existing study so far that is used to see or to understand how much of the battery energy storage is required to first have the minimum hosting capacity, and second, to have a improved hosting capacity, depending upon the DER mandate. The second part of the second question related to the quality. Well, that's a very good question. So in the US, what we have currently is the two check. One related to standards and how that quality of those system is connected through the standard. So for example, IEEE 1547 is a standard that is used to mandate distributed energy resources interconnection to the power grid and the associated related quality checks, which is basically the frequency quality and the voltage quality and the changes in voltages with respect to the interconnection when it is connected and when it is islanded intentionally and unintentional islanding and things like that. So that is basically on the standard level, which we have a check on the quality. The other part is what we call it interoperability, which makes sure that each of those devices which is plugged into this system should have a feature that allows that it is plug and playable. Which is not directly related to quality, but it helps improve the quality, because if we have that plug and playable feature associated with it, the problems related to, so quality issue comes in two forms. One form is the device level problems and the quality, like for example, harmonics and the device induced issues related to that. Second part of the quality is related to the sensors and the instrumentation associated with the device and the capability of those sensors and instrumentation. So the interoperability standard, which makes the integration of these devices in a common platform, help to improve that second part, which is the instrumentation. So that's what we have currently established. With respect to the working with the field with the Duke Energy, these checks are still not enough. So there are some initiatives done in the IEEE level now, I guess, to improve this. I hope I kind of gave you
one small question also. For the future, battery is going to be a very, very important parameter or storage devices. But other than battery, there could be some other storage systems, maybe pumped hydro or the thermal storage, gravitational storage. So many could be there, So what are the possible candidates? I mean, could be economical and feasible.
So two main type that is very importantly being used these days, especially in the US. One is related to flywheel-based energy storage. So there is a specific type of flywheel, not like a big flywheel. It is a magnetic energy-based flywheel storage system that can be done on the distributed manner, meaning small scale, small flywheel-based energy resources. I think that is picking up. That is actually mainly for active power management and the frequency response related to that, because it has got a fast recovery time as opposed to the battery energy storage. So that is one candidate which I think is up and coming. It used to be associated with the wind farms on the bulk level. Now it is moving into the distributed energy resource on the power distribution sector. And the second one is the newer version of pumped hydro. I wanted to say newer version because the pumped hydro in general, we used to have a conventional hydro systems and a small scale associated with that. That pump hydros are actually used for peaking power plants, as you may remember in the olden times. Now this has been connected with the power electronics devices which a fast recovery time. So that's the second candidate, which is all of them are actually the main challenge is on the DER, distributed energy resources related. I am not sure. I think there will be also a very important candidate which is probably coming up within the e-mobility space with respect to the vehicle charging and how we can utilize these resources to charge and discharge at a specific time. Personally, I think that's dear to my heart. I think that's something which is also going to come up.
Okay, sir.
Yeah, sir, can you just say something more on PMU and our systems, that smart grid and supporting PMU on the systems?
In general, about what is PMU and how it's been used, or in specific to any application?
PMU, okay, but how it supports our system stability or grid stability?
Oh, yeah. So see, there is a big shift between model-based management of system and measurement-based management of system. Model-based management system, basically, we used to model the system, and the modeling of the system are not very dynamic, right? You cannot get a very changing or dynamic model. So the stability and management of the system, if you have a measurement-based modeling, that is even better, measurement-induced modeling. The challenge was that we never used to have a device or a measurement device that is very accurate and very fast. Phasor measurement unit to give that opportunity. We can, but measurement-based has got more accuracy and more controllability and ability to manage the system. So that's a trend.
Thank you, sir. Thank you.
So coronavirus pandemic has changed.
There are actually a couple of questions in the chat box.
Yes. Do you want me to read it, or do you want you to read it, or I can?
Yeah, somebody can read it, Akshay. Read it.
Yeah, I will read it out. Coronavirus pandemic has changed the energy use patterns because of reduced mobility and stay at home. How has this impacted the duck curve? Does that lead to more smaller solar home units back feeding into distribution circuits?
Well, that's a good question. I have not seen any change with respect to the energy pattern a lot at the pandemic, during pandemic rather. There is obviously the shape may be a little bit larger or smaller depending upon people staying at home and then work like that. But the duck curve is mainly an attribute of photovoltaics or the photovoltaics induced in the system, whether it is behind the meter or in front of the meter. So that actually is not necessarily related to pandemic. It is related to whether people are using whether photovoltaics in the system or not. So so basically duck curve is you can attribute that towards solar homes being there or not. So smaller solar homes or larger solar homes, I don't think pandemic has an impact on it. Obviously, there will be an impact related to cost, and people may be whoever has been decided to go for solar homes may now rethink or may go with the smaller homes. There may be some impact. But other than that, I don't think, honestly speaking, I see any change in the shape on the duck or such. Now, the second question on the pandemic, would you say that pandemic has been a catalyst for future of renewable energy resources? The renewable energy resources integration is actually a two-part problem. One, obviously, it's mandated or pushed to become more sustainable and to avoid any climate change related aspects or like that. That push or that mandate is going to be there throughout, whether it's with pandemic or without pandemic. Now, whether the pandemic effect has supported this initiative or not supported this initiative, I think there's only one factor that is coming in fray, is that whether we have enough resources now to do that support in the form of money, or whether we want to shift our focus to save our lives before we move that. So there may be some delay there, but other than that, I don't think there will be a significant impact. Which is the least implemented renewable energy and why? The least implemented, I don't know the answer to that. It depends upon the type of the locations and the type of the systems in different part of the world. The most likelihood candidate which technology-wise has been improved is photovoltaics and wind farms, as you already know. The reason of having these photovoltaics and wind farms coming in the forefront depends upon the technological push to have these renewable energy resources supported and the capability of these technology resources to move faster or move forward. There were other candidates which as you may know, related to renewable energy resources, such as geothermal, and those resources are still there. People are still working on the technology. The offshore winds is another one. Wind wave technology is another one. But the dependency of these technology, depending upon the location, is the biggest factor to me, not about the technological advances. Sources are actually located in different plots, right? For example, the photovoltaics as well as the wind farms, they are universal. You'll see everywhere. So it will be, you can move the technology faster. But other technologies, it depends upon the resource location. So you will not have that kind of visibility with respect to the technology changes or advances. So I think the main factor related to that is not necessarily the technology change or push, but the energy resource availability, if that makes sense.
I have a small question. You were mentioning about flywheel energy storage, which is coming up in a big way. Can you please extend some information about are the flywheels kept in vacuum and the possible size of these flywheel energy storages?
So the flywheel energy storage is basically the rotating mass connected to for example, a motor or the device. There are two parts for the flywheel. One, obviously, you should have less losses on the connecting rotating mass, and you should be able to generate that energy coming out from the flywheel with less losses, right? So that is why we will have a magnetic gear and magnetic related aspects on the gear part from the sources that is connected to that flywheel. That is one aspect. Size-wise, it depends upon there are two factors. Obviously, the speed, if you increase, you can reduce the sizes. Now, when you increase the speed, it comes with the capability of the material that can sustain that speed. For a high speed, for example, 30,000 RPM or 50,000 RPM, you should have a material that can sustain that speed. And if you have a magnetic related gear there, you should have, we will get into what we call rare earth materials, which is very, of course, pricey. but the management or developing of the architecture, the design is critical. But if you increase the speed, you can reduce the size. And that is what the technology advances. Just to give you a flair of, we were actually part of a couple of projects from a company. If you're interested,
that is fine. My one question is: are they kept in vacuum? Flywheels?
No, you don't have to. You don't have to.
Earlier we were talking about flywheels in vacuum. That's why I asked.
Correct. Yeah. So there is a few technology that has been coming up now. There is a couple of companies in the US who is now becoming a big player in here. They have a few method to have these energies, flywheel energy storage without vacuum.
Thank you.
And you know the problems related to vacuum, right? I mean, it's just
Thank you. Fine.
And I can share some
all the comments
related to that if you are interested.
I wish to make a small comment. That was a very informative talk by Dr. Kamalasadan. Actually, with the large-scale integration of renewable energy, climate change, so many new things are evolving in the power system. System planning, operation, management, undergoing big changes. In this context, the new way of thinking the power system management is really deserving a lot of importance. I think the students, the researchers, and teachers will benefit from this kinds of talk, because to appear in the textbook, this latest information, it will take a long time. We had a talk last week by Dr. Shaib Braham, the vice president of PES. She was talking about resiliency planning and climate change. So these are all new terminologies and new approaches, and we need to be familiarized with the new trends in the power system planning. And thank you for updating or informing us of the new trends. And I think it will benefit the new generation of power system planners and operators. Thank you.
Thank you.
And also, I think, sir, the AI and IoT, everything will make the smart grid more and more smart, isn't it? And it is smart with the more and more distributed energy, especially the photovoltaic. I think the smart grid is an integral part of the grid itself. I mean, without smart, it cannot work at all. Yeah. So it's a very hot subject, not only for the industry, also for the academy. So definitely it was a very, very useful talk for most of us present here. And thank you, sir. And let us go to next vote of thanks, Akshay. Akshay?
Okay, sir, sure. Well, before that, first of all, thank you, sir, for being with us amid your busy schedule. In recognition of your effort and presence, we would like to present you with a virtual memento. Please accept it.
Yeah, sure. Okay. Yeah. Okay, sir. Yeah.
Okay, so now it is time to capture this moment. So I request everyone to turn on their cameras so that we can have a virtual photograph of this session. So everyone, please.
In 3, 2, 1. Done. Thank you.
Thank you all. Now, to deliver the vote of thanks, I invite the Secretary of IEEE PES Kerala Chapter, Dr. Bobby Philip. Over to you, sir.
Thank you, Akash. Sorry. Good evening, all. Respected Vice Chair of IEEE Kerala Section, Professor Muhammed Kasim, sir. Respected Chair of IEEE Power and Energy Society Kerala Chapter, Suhair, sir. Respected Chair of IEEE Education Society, CM Varughese, sir. IEEE PS Kerala Chapter Founder Chair, Dr. PS Chandravan, sir. I think am I audible? Am I audible? Okay, thank you. So, first of all, I would like to thank Professor Sukumar Kamalasadan, sir, for having agreed to deliver this talk and enlightening us with rich knowledge with regard to renewable energy, distributed energy resources, system resilience, and with the new trends in e-mobility, the integration of electric vehicles and other type of non-linear loads, and associated trends in research and development in these areas. And it was nice to see that a lot of developments, interesting developments are taking place, which can actually transform the shape of the grid that we have been seeing for years. We can see that the interaction with the grid by different devices and the measurement of different quantities like synchrophasor measurements, and even the distribution side also, different kinds of measurement and sensing devices are getting integrated. And we could see from his presentation that the system, the whole system is now becoming a system of systems. And distributed control concepts are more and more getting included in the architecture. And it was quite enjoying and enlightening lecture, arranging the ideas in a beautiful and yet simple manner such that even a layman could be understanding it. And we, on behalf of IEEE PS Kerala Chapter and IEEE Education Society Kerala Chapter, would like to thank Professor Kamalasadan, sir, for this nice talk. And in fact, this, whatever things that has been presented, would greatly enrich our knowledge in the classroom discourses. And also the student community also got benefited by getting an opportunity to know the state-of-the-art developments that is taking place in this area. So once again, on behalf of the organizers, that is IEEE Educational Society Kerala Chapter and IEEE PS Kerala Chapter, we express our sincere gratitude and appreciation for having agreed to deliver such a very timely topic, a talk on such a very relevant topic, and that has helped us to update our knowledge, as the eminent speakers are, those experts who have mentioned these things already. I once again thank him for having agreed. And next, I would like to thank the leaders, especially the IEEE Kerala section Vice Chair, Kasim sir, IEEE PS Kerala Chapter Chair Suhair sir, and the Education Society Kerala Chapter Chair Varughese sir for working behind the scenes to arrange this talk in this manner. And also I would like to thank Chandravan sir for joining the discussions. And also I thank all the participants and students who were present today to listen to Professor Kamalasadan sir. Thank you, sir, and good night. Thank you.
Thank you so much, sir.